Welcome, everybody. It's Tuesday, it's 1 o'clock. We are back from the HUG event in Europe, and that means we are back to normal, to our HDF clinic, although today might be a relatively quiet one because there wasn't too much traffic on the forum. Anyway, let's get started. Are there any questions? I checked our Google document. I didn't see any questions there, but are there any questions right now?
No questions for now, Gerd.
Okay, thank you. Welcome. Okay, last week's highlights, or last 2 weeks. No, it was just last week's highlights. We released HDF 110.9 and the usual what we had in the release candidate already. Parallel compression improvements. There is a Doxygen-based user guide draft included. And HDF5 is now tested on macOS with the M1 chip. And then something that came up in a release notes is that, yeah, after 2022, so beginning in 2023, we will no longer support Visual Studio 2015 in the different HDF releases. Other news, yeah, the VFD Swimmer Beta 2 release is out, and we haven't really gotten a lot of feedback. Probably, yeah, everybody's busy, but we would really encourage for anybody who is using Swimmer already, the earlier, the original Swimmer implementation. But yeah, we would encourage everybody to test that and give us feedback, see if there are any issues, and if performance is as good as with the previous Swimmer or better, hopefully. And so yeah, if you have time, please check that out. The European HDF User Group meeting was a big success. I think some of us traveled there, and yeah, it was really, for me, it was the first in-person event, sort of post-COVID, if we call COVID over. I'm not so sure about that, but it was definitely great to see everybody in person over there. And yeah, definitely thanks to the organizers who made this happen. Stay tuned. We recorded the presentation. Some of you might have been able to join online, but yeah, the presentations were recorded and will be available on our YouTube channel sooner or later. We are working on that right now. Okay, I think that was it for announcements. I'm going to pause. Any questions so far? No? Okay, then I'll just press on with the forum. There wasn't that much happening on the forum. There was a little bit of an update on the FlatHub. Remember, FlatHub was that thing. My understanding is it is a way of packaging software on Linux in a sort of distribution neutral way. And someone suggested, well, wouldn't it be great if we could take HDF View and distribute it that way? And there was, and there were no contradicting voices. I think there were only people who are saying, great, let's try. Whoever knows how to do that, let's try it. And there's been some progress. I think the person who initiated that thread posted some progress, including a link to a GitHub repo, I think, where they are preparing a pull request for this. And the comment that they left, though, is a little obscure. The person was saying mostly working except file system portal integration. I don't know what that means, which makes the entire thing pretty useless for now. The code may need patching. So I'm not sure what that means. I've never created a FlatHub package, but yeah, I'll keep an eye on it and see where this goes. And then there was an update on HDF5 on this thread, remember, where we were looking at HDF5 write performance. We were looking at direct chunk writes with H5D write chunk, and then writing to a chunk data set with H5D write, and then versus writing to a contiguous data set and trying to explain the difference in performance. And the creator of this thread, Samuel, actually posted pprof profiles. I need time to digest them, but actually just before this meeting, I tried to load them into kcachegrind, but then kcachegrind wasn't happy with the formats because I think Samuel might have forgotten when he ran pprof, there's an option -- call-grind, and he may not have specified that. And if you don't specify that, then the output format is different from what kcachegrind or it's the so-called call-grind syntax. The formatting is different from that, and then kcachegrind just complains and says, I can't read that. I think it says something like no access to the file, but that's bogus. It just can't parse that file. Off the top of my head, I'm not aware of if there's a converter tool available that can convert the default, which is the non-call-grind format, into call-grind format. So I haven't done that. So I really tried that just literally before this meeting without success. But yeah, then even if I could do that, yeah, I would have to stare at those graphs for a moment in kcachegrind to understand what might be happening. I don't know, has anybody here tried to look at those profiles? No? Okay, yeah. So it's just something we'll get to eventually. Actually, Samuel was there at Hug, so I saw him there in person. And yeah, but he hadn't yet posted these profiles, I think, so we didn't get a chance to talk about this. Okay, that was it for the forum. There were some other issues around compilation and whatnot, but nothing that caught my attention otherwise. And I'm going to pause here again, see if there are any questions. Otherwise, we can talk about a problem that we discussed at the workshop, actually, that someone raised, and what our conclusions were. Any other questions?
Gerd, just one. This came up a little bit in the at the conference, and it had to do with the presentation on the Onion virtual file driver.
Yeah.
And in terms of storing the deltas, and I noticed Lucas had asked a question about the deltas, about the delta versions being stored in the intermediate checkpoints, and I'm looking at the PDF there, but because I was wondering, are the checkpoints done at the data set level or at the attribute level, trying to get a feel for what the granularity of the checkpoint was? But from your document, it sounds like it's actually at a very low level that the deltas are stored. It's not, and you can't think of it in terms of a data set checkpoint or anything like that. It's at a much lower level than that.
Yeah. That's my understanding too. I mean, I haven't really spent much time sort of analyzing and digesting that. But I think, yeah, it is at a very low level in the sense that when it's basically, so if you just think about the structure of an HDF5 file, the structure of an HDF5 file, you can think of it as a stream of messages, so to speak, that is interleaved with raw data, what people call raw data, sort of the data set elements that are stored in these things that we call data sets. So that's the structure of an HDF5 file. Now, if we make changes to such an HDF5 file, by default, these changes are made in place. So, for example, if you change the value of a dataset element, well, yeah, that takes place in place. So the value where the old value used to be will be replaced with the new value. Or if you delete a link, for example, then yeah, there is some data structure in the file that represents the links of a group, and that heap, in this case, that link will just be removed from that heap, and everything is good. Now, with Onion, of course, that doesn't quite work like that. And because with Onion, once we have sort of that baseline file, that initial file, that is from then on, in a way, read-only. And all the changes that we make to the original file are written to this checkpoint file, or the diffs, if you want to call them that, are written to this checkpoint file or to this diff file, and yeah, the original file is read-only. Now, my understanding is that for performance reasons, well, first of all, the contents of this diff file, so to speak, they are not HDF. They are not HDF files. So this is not an HDF5 file. So the implementors of the Onion VFD took some liberty there to really optimize the format of this diff file for that purpose, which means to capture the difference between a baseline HDF5 file on top of which you then layer differences. So for example, and I could be wrong on this, but I believe this diff file is, for example, organized in pages. So even if the original HDF5 file, for example, doesn't use a feature like paged allocation or something like that, I think for efficiency, the diff file is organized in pages. So you don't write sort of arbitrarily sized updates. You typically do that in pages. And now you could say, well, what's the size of that page? I don't know, but I believe that's the case. So and the contents of this file would be essentially, they would be essentially what happens when you make a change to a data set. So when you make a change to the original HDF5 file. And so the picture that you should have in your head is basically, and we've spoken in the past about this, that the state, if you wish, of an open HDF5 file has two parts to it. There is the part of the state that's reflected in bytes on disk, and then there is a part of the state that's reflected in memory data structures, in particular the caches, the metadata caches and the dataset caches and so forth. So let's say, for example, I delete a group, or I add an attribute or something like that. What that would typically mean is, before that gets persisted in the file in bytes on disk, it would linger for a while in the metadata cache. So that would be now in the Onion VFD scenario. What that would mean is that since we cannot write that attribute to the original HDF5 file, we would have to stash it away in this Onion file. So there would be definitely an entry in this diff file or in this Onion file that would basically have to keep track of, okay, in the case of an attribute creation, for example, well, which object was modified in the sense that an attribute was added to it. And sure, if the object existed already in the original file, we can make reference to the original object header and say, well, this is an object that was in the original file, and we just added an attribute to it. But then, of course, the serialized attribute information would probably look very much the same as if we had flushed it into, or updated, written it into the original HDF5 file. But then, for example, let's say we create a link that changed the destination of a link, for example. It would be a similar thing. Now, what's interesting though is, and I don't have an answer to that, is how do we, but yeah, the Onion implementers have done that, obviously. You would have to indicate and say, okay, the original link that's in the file, that link is no longer valid. And rather than using that original link, here is a new link. Now, so what that means, for example, for the group structure, I don't know to what extent information is copied into that diff file. So, for example, if we modify a group, is the group maybe in a lazy fashion sort of copied over into that diff file, and as we make changes to it, it's updated or it is persisted in that diff file? I don't know, or if it's really done at the link level or the heap level. So I don't know how far this is broken down. And yeah, so I can take that as a homework to either read up in the specification or ask one of my colleagues to enlighten me on how exactly this is implemented. Because I mean, definitely. So let's say, for example, we talked about a data set. If you have a like 100 gigabyte data set or even 100 megabyte data set, and we are changing just one, and it's contiguous, and we are changing just one value, we wouldn't copy over that whole 100 megabytes. But then you have to make a decision where, well, okay, if you change one value, then yeah, just storing that new value as a patch where you say, well, when you read back the data set, you have to basically, you can read the original data set, but then you have to patch on top of that one element, and the new value is here in that diff file. Whereas if you modify a hyperslab or a larger contiguous region, of course, that would have to be stored in that diff file, plus the reference information that says, well, yeah, this is sort of the original data set, but then this region in the original data set was modified, and yeah, and so yeah, it's tricky business, but yeah, it's definitely done at a very low level.
Yes, but it's the Onion VFD that takes care. If I'm sitting at, let's say, just an editor, and I want to look at these previous versions, the Onion VFD takes care of reconstituting the intermediates if I were to choose to go back.
Yeah. I mean, in a way, it is probably much simpler than I'm imagining right now, because once you are at the VFD level, the HDF objects are gone. All you see is basically byte ranges in a file where when you write a VFD and your VFD gets called, all you get asked to is, okay, at this offset, write this many bytes, or at this offset, read this many bytes, and so forth. So this is the level at which we are here. And so what we have to now do is in a way only trace where so the simplest structure of this diff file would really be every time the Onion VFD sees a write, we have to basically keep track of, well, yeah, at which offset, what was written at which offset. And this diff, we would have to stash away in the Onion file, so to speak. And and we have to make sure that when we read from that updated file, so to speak, we have to look at from which offset we have to read which byte range. And then we have to basically do, if you wish, a range query where we have to say, well, were there any updates in this byte range over the original file? If there weren't any, then we just go to the original file and we just read from that offset and read those bytes. Whereas if there was an overlap between that byte range and one or more updates were done on top of that, then we have to sort of, yeah, parse out which bytes are sort of the current bytes, so to speak.
Yes, yes.
And that's in a way it. So in that regard, it's probably a lot easier than we think, in the sense that, yeah, at this point, everything is just bytes, and we don't have to speculate about, is this a data set or is this an attribute? Or the VFD doesn't know anymore. The virtual file driver doesn't know anymore what something is. It's just bytes.
Okay, that makes sense there. I get that.
Yeah, yeah, and I think that drastically simplifies the implementation, because, yeah, you really have to just keep track of byte ranges, but still the idea of in a way superimposing sort of a raster of pages makes it then easier to track those changes, because then you can coarsen the granularity rather than keeping track of each offset and range and so forth. If you project this on or if you superimpose a paging of the original file, then you basically can keep track of, well, which pages were modified, and so everything becomes a little more scalable because you're maintaining it at, let's say, a 4 kilobyte or 1 megabyte. I don't know if that's configurable in the Onion VFD. Probably not, but it might be a compile time constant. When you build the Onion VFD, I haven't looked at the code in the header file. There might be a setting where you can set that page size, but again, don't quote me on that. But I seem to vaguely recall that when this feature was discussed, people were saying, yeah, we do this sort of on a page level to just, yeah, keep it a little more manageable.
Okay.
But it's really just bytes. Yeah, I think that's, now that I think about it, that's the thing. It's just bytes at this point. There are no objects.
All right.
Yeah. Okay. Thanks. Yeah. And I hope, I don't know. Yeah, I'll go back and look at the RC, how into what level of detail the RC goes. But I think this is also a good example where sometimes drawing a picture actually doesn't help, because it makes you think, oh, this must be very complicated, sort of maintaining all these pointers and whatnot. But that's not what happens. It's really brute force. It's a byte stream, and you have to keep track of where was the byte stream modified. And that's it. And yeah. Okay. Any other questions? No? Okay, then I'll briefly talk about tips, tricks, and insights. So one, in the discussion there, one of the attendees was asking, and this has come up many times in the past, is people would like to create compound types, so record types, if you wish, where they run into this issue where the library comes back and says, oh, I can't create that, there are too many fields. And so the first question would be, Why is that? Why would there be a limit on the number of fields? And the reason in this particular case is, as we just discussed, if you look at sort of the byte level representation of a compound type, for example, or any data type, not just compound types, there is a message in that sort of stream of messages in the HDF5 file for a particular data set or an attribute. There would be a header, a so-called data type message that would, in a way, when you parse it, tell you, oh, this is a compound type, and this compound type has this many fields. And then for each individual field, it would tell us what is the name of that field, what is the data type of this field, and so forth. Now, unfortunately, the size, when all this was designed, the size of these data type messages is limited. It's typically a few kilobytes. And in this particular case, since the field name, for example, is stored as part of this message for a particular field, of course, the easiest way to provoke this. So you could even, I haven't tried this. If I had more time, I should have done this as an exercise. I think you can create, it's not so much a question of the number of fields. If I create a compound type with one field and I make the name many kilobytes long, the library may be unable to create that for me because the name just doesn't fit into this. The message then would exceed the limit and it would fail to create that data type. So you can also try the opposite, give your fields very short names, just call them 0, 1, 2, 3, 4, 5 and whatnot, and you might get away with that. But at this point, it's really a limitation in the file format. So could that be fixed? Yes, absolutely. It could be fixed with a file format change. But then that's something, of course, that is rather intrusive and invasive, and we try to avoid that. And of course, yeah, okay, this was, I think compound types were there from version 1 from the very beginning. And at that time in 1998, whenever, yeah, nobody thought that people want to create compound types with 10,000 fields or something like that. I think that wasn't really considered a common use case or something like that. And even today, I'm not sure. I mean, do people use record types with that many fields? Yes, they do, but is a compound type in HDF5 really the right way to model that? I'm not sure, because it then depends on, well, how do you access, for example, this compound type? The only, in a way, legitimate, in double quotes, use case I could see was, or would be, if you said, okay, I'm reading all the fields of each record all the time, because then, yeah, there would be no access penalty, in the sense you wouldn't be reading too much data, and then throw away half of it, the fields that you are not using. But that's kind of an extreme case. But okay, be that as it may, the question is, are we doomed at this point, or are there ways to get around this limitation? And the answer is, as so often, I would say almost always, there is a way, or there are multiple ways to get around this limitation in HDF5. Number one, the easiest is divide and conquer. You could say, okay, I can't have my 10,000 fields, so maybe I can break it down, and 10,000 is maybe a little extreme, but let's say a few hundred. You can break it up into multiple compound types if you want to maintain that appearance of a record. And then, okay, instead of having one data set, you would have maybe a dozen or a few dozen data sets. Not pretty, but maybe workable. It really depends on what you are trying to achieve. Another one that would be sort of the extreme columnar approach, so to speak, And by the way, of course, one of the limitations of compound types is once you've settled on a set of fields, you can't change that. You can create a new compound type and add fields or remove fields, but you cannot modify an existing compound type. Whereas with this sort of second solution or the second workaround, if you create a group that's kind of a stand-in for a data set proxy, or is like a data set stand-in, and then you make each field a separate data set, then there is no limit. You can keep adding columns, you can keep adding fields as much as you like. Now, a downside of this approach would be, well, first of all, the record type would now not be represented as an HDF5 data type. If that's what you want, then that wouldn't be the case here. And of course, there could be performance issues here. For example, if you have then all these columns, you would, if you wrote just one record at a time, you would have, and let's say you have many dozens or hundreds of fields, you would do all these small writes to these data sets. So without any kind of buffering and so forth, the performance of that probably wouldn't be good. So there is a downside here. I think there's no solution here where there are only upsides or advantages. The third approach would be to say, okay, your record gets somehow delivered to your application, and you could say, okay, I'm just going to treat this as a blob, as a sequence of bytes, but I'm going to retain some metadata that allow me later to then parse this blob and really extract individual fields or extract the whole structure. Again, it's a solution. I don't see much of a downside in terms of performance other than on read if you want to selectively pick out certain fields. In this case, certainly you would have to read everything and then for each row parse out the fields that you are interested in, unless it's sort of fixed size and you can sort of do strided reads where you have the same offset in each field and so forth. That might speed things up a little bit. But then that goes back to the original problem. I could see a legitimate use case for these large numbers of fields only if you consumed on read all the fields for all the records that you are reading, because otherwise you would be losing performance anyway. And then the fourth workaround might be you could use multiple 2D data sets, and which could also be extendable in the sense that, so if you have sort of dozens and dozens of fields, then there's a good chance that the data types of these different fields, they are not all different. So let's say you have 5 different types. You have floats, integers of different lengths, and maybe a fixed size string or something like that. So what you could do in that case is just create separate 2D data sets, one for each type. So one for the integer or multiple for the 8-bit integer, the 32-bit integer and whatnot, and then one for the double precision floating point numbers. And then in there, you would have a 2-dimensional data set because each column would represent a field in your sort of abstract record type. And it's, of course, the downside here is you would have to track separately in attributes, for example, which column in this 2-dimensional data set corresponds to which field in the original record type. That's okay. But an advantage with this approach, if your 2D data set were extendable, you could actually add fields over time. You couldn't easily remove them, but if you had to extend such a 2-dimensional data set, that would be an issue. And yeah, and you could use compression, and it probably would compress better than the original large compound data type where everything is sort of mixed together. This approach might actually compress better. And yeah, so these are the 4 options that I can see to work around this problem. And yeah, so that it doesn't look, I mean, it certainly doesn't look as pretty. If your requirement is, I want to open this in HDF view, and then, well, if you have 500 fields in that data type, good luck with that. That's not going to look pretty in HDF view for sure. But yeah, so if you are focused on this has to look like a record in any kind of visualization application, well, yeah, then I think none of these workarounds is going to satisfy you. But then, yeah, I'm not so sure how common these gigantic record types are. Okay. So, and we are over time already, I'm sorry, but yeah, that was it for today's tips and tricks. And yeah, we'll be back next week. Hopefully I'll be over my jet lag and yeah, have something more interesting to say. Okay, take care. Thank you.
Thanks, Gerd.
Mm-hmm.